right, we're live. Hey everybody, let's do the practice final. So, let's see, I got my pen here, draw a bunny. Are we all on the same page? I don't know if anybody's going to be online yet. Nobody's watching, but if anybody does come online and ask questions, I can answer them. So the deal here is you're better off trying the final before listening to me rattle off how and why each question is, but do your best. Okay. So the final here and in general will be sorted into short answer, medium length answer, and long answer questions, each worth a different amount. I have it in front of me. Obviously, you can see it. The best way to do one of these exams, I mean, you've seen your share of exams, is to start by reading through all the questions first. You know, probably take you 10 minutes, but it's going to be 10 minutes really well spent. So you read through and you're like, oh yeah, okay, that makes sense. Okay, right. I see. Oh, that's good. Oh, this is going to take a little while. That question's tricky. Oh, and there's constants here and scrap paper. Okay, so I can use this last page. And maybe it's got some constants that Dr. Tippett didn't write down here. Anyway, so got it? And then once you have a sense of the lay of the land, go through and do the easiest questions first. You always want to do the easiest questions first because essentially it goes like this. You studied really hard. You understand all sorts of stuff. If you do the easy questions first, those are easy marks you put in the bank. It's like a game show. You want to get as many questions for sure done as possible, as soon as possible. And after that, even if there was a question you had trouble with when you first read it and you're trying to think about it, your brain's going to be working through how and why to do it. And so by the time, 2 hours will have passed, you get back to that question, you'll be able to do it. Or at least you'll have a way better shot at being able to do it. Your brain will have been thinking about different things. And what is it? The l'esprit d'escalier, the spirit of the stairwell when somebody says something rude to you and you would try to say something back, but you can't think of anything to say, and then an hour later you're like, oh, I should have called that guy a butt. Yeah, so it's like that. You essentially want to harness l'esprit d'escalier and put that to work. Okay, so, but I don't need to do that because I wrote this test. So I'm going to do them in order because presumably you've tried it already, and what we're doing right now is we're marking the test. So hold on a second. My internet's kind of weird, so I'm going to futz with something for a second. See if this works. Okay. And I think we're back. We're back live. Yeah, okay, that's better. Okay. So like I said, I'm not doing the exam in front of you. I mean, I will be. I haven't seen these questions since I wrote them last week. But essentially, we're marking them. So don't expect that you will be doing these questions in the same order as I am doing them, because I wrote the test. And so I know what the answers are. Well, I don't know what the answers are, but I know how to find the answers because I taught the course. Ooh, that tea's hot. Okay, so let's begin. Electrostatic equilibrium means there are no charges moving, or there are no electric fields inside the conductors, or electric fields near the surface of the conductors or perpendicular surface, or all of the above. Well, electrostatic equilibrium is usually used in context of metals and conductors, so it's probably got those. You know what? It's all of the above, because each of these are true. That's how you know when your system is in electrostatic equilibrium. Time for the next question. Consider the following situations where the electric field lines are drawn near some charges. Oh, the charges are in black on my page. Determine the total electric charge missing in the missing region. So the way we're going to do this is we're going to rely on a trick that you learned when you were drawing these pictures, which is that the number of lines is proportional to the amount of charge. The more lines there is, the stronger the charge is, in other words. So let's just check to see here. This one has 1 coulomb, and it's got 2 Oh, hey, look, there's a mistake. It's got 2 going into it. And then this one has 2, and it has 1, 2, 3, 4 going into it, coming out of it, because it's positive. This one's 4, and it's got 1, 2, 3, 4, 5, 6, 7, 8. Okay. So it's going to be the number of lines divided by 2. So each coulomb has 2 lines coming into it. Okay, so this one has 1, 2, 3, 4, 5 lines in, and 1 line coming out. So it has 4 lines going into it total. So that means there's 2 coulombs inside the box. Considering the false situation with negative charge has been placed at location A, draw the direction it will feel the force. Okay, so the question is, how do we interpret these equipotential surfaces? The idea is that the force isn't going to be in the direction of the line, so it's not going to be like that. Here, let's draw 4 examples. Okay. So of these 4, which can be true and which can be false? It's not going to be these 2, because it's not going to be parallel to the lines. It's going to be perpendicular to the lines. You can think of these as like lines going downhill or uphill. Okay, so it's a little bit more tricky than that. So this direction here is the direction of decreasing V. As V goes down, the electric potential energy goes up. Wait, no. All right, hold on. If Q is positive, then the potential energy goes down and the kinetic energy goes up, which means that for a positive charge, it's going to feel a force in decreasing V. This one's a negative charge though. See? Negative charge. Negative charge. And that means instead of feeling a force in this direction, it's going to feel a force in this direction, in the opposite direction, because Q in this case is going to be negative. So Q being negative, delta V goes down if we move to the right, but this number is going to go up. And so the kinetic energy, instead of going up, is going to go down. I hope that made sense to you. Me rattling it off like that. The deal here is that negative charges feel a force pointing in the increasing V. If you want to learn it as a rule of thumb, that works. If I take a parallel plate capacitor and leave it plugged into the battery and double the area of the plates, will the electric field between the plates double, half, stay the same, or it's impossible to tell? Well, let's reason this through. Okay, so it's plugged into the battery. Okay, so that means that after you make the change, the potential energy is going to, or the electric potential between the two is going to be the same. I taught you a bunch of different ways to reason this through. Let's reason it through visually, because that's fun. All right, so if before there was 3 lines between it, afterwards there's still going to be 3 lines between it because the battery hasn't changed. Now, the electric field strength is dependent on how far these are apart, right? Now, it's the same distance between them before and after, so the electric field before has to be the same as the electric field strength afterwards. And it's asking us about the electric field between the plates. So it's going to stay the same. Stay the same. Okay? Okay. If I take a parallel plate capacitor and after unplugging it from the battery, half the distance between the plates, will the electric field between the plates increase, double? What's the story? Okay. So let's draw it before and after. Okay. So let's narrate our way through this. I've unplugged it from the battery, which means that the charge on the plates is going to be the same. Q initial, Q final. Same amount of charge. Okay. Now, the electric field is equal to the charge divided by epsilon naught times A, because it's equal to the charge density over epsilon naught, right? So because the charge is the same and because the area is the same, the electric field strength will be the same in both cases. Oh, hey, that's what it wants to know about. Okay, so it stays the same. Weird, huh? All right. And if you can't follow what I just told you, well, then go relearn how to do that reasoning like we did on the midterm. I taught you 2 different ways to reason through these problems. So try to remember how those went. Next question. If I assemble a circuit with a battery and a capacitor, and I leave the battery plugged into the capacitor for a long time, inside the wire, which of the following statements is true? Let's draw a picture of this. Boop, boop. There's the wire. There's the capacitor. Here's the wire. Here's the capacitor plate. Okay, so I leave it plugged in for a long time, so charge gathers on this plate and charge gathers on this plate. So the question is asking about the wire inside here. Which of these is true? Is the wire in electrostatic equilibrium? Yes. Is the wire in, all right, so let's put a check mark because I believe that that's true. Is the wire in dynamic equilibrium? Not really-ish, no-ish. I mean, I guess technically V is equal to 0 is a velocity, but I mean, nothing's changing in it. So, because the charges aren't moving, so it's not dynamic. So I don't think that's right. C, there will be a slight potential drop across the length of the wire. Is that true? Well, if there were, then it would mean that there would be an electric field inside the wire. But the electric field has to be 0 inside the wire because it's in electrostatic equilibrium. So this one can't be true. B and C are both true. Well, C is definitely not true, so that's not it. It says to choose one, so I'm going to circle that one. Next question. A charge is placed at rest in a magnetic field. Will it speed up, accelerate but not speed up, feel no force, or move towards the north side of the magnet at a constant velocity? Well, okay, so the force it feels is QV cross B, right? Oh, it's at rest, so V is equal to 0. So the whole force has to be 0, so it doesn't feel any force. Oh, hey, there's lots of trick questions in this example. That's weird. Okay, a ring is placed inside a magnetic field as shown. If the magnetic field strength is decreasing, sketch the direction of the current in the ring. Okay, so there's X's here. The X's are disappearing, so the flux inside this ring is decreasing. What's the current going to try to do? The current's going to try to make its own magnetic field that replaces the missing flux. It's going to make a magnetic field pointing that way. Which way does the current have to go? I'm going to use my right-hand rule. I'll draw the right-hand rule in this case works like this. Take your fingers, point them in the direction of the magnetic field with your right hand. Wrap your fingers around the bar in this case. There you go. And now your thumb points in the direction of the current. So it's going that way. Regarding energy, magnetic fields, do they never give charged particles energy? Yes, I think that's true. Do they speed particles up but never slow them down? No, they don't speed them up. Do they sometimes do work? No, they don't do work. Do they do work on things that make a magnetic field with aren't charged particles? This is a fun question because there is nothing that isn't... all magnetic fields are caused by charged particles. All magnetic fields are caused by charged particles doing a thing. So the answer is here. They never give charged particles energy. You can tell that I wrote this test in about 45 minutes because all the answers are kind of trick questions. They won't all be no when I give you the final exam. You can count on that. Okay, a rock of mass m sits inside a hole x equals 0, and I push the rock a little distance away from the center, and there's a force pushing it back towards the middle that looks like this. Okay, so this is simple harmonic motion question. Do you remember how that went? The idea was that the motion could be described in terms of a position as a function of time. It goes like this. Your farthest out position times cosine times a number times t. Okay? What's the number that goes here? The number that goes here inside the terms of frequency is the square root of this number. It's the square root of 16. Just ignore the sign. That minus sign needs to be there for simple harmonic motion, but just ignore that number when you're calculating the period. So this number here is a 4. So what's the period? The period is the amount of time for 4t to equal 2 pi. So it's going to be t over 2 pi divided by 4. That's pi over 2. Or this answer. Okay. Not this. If you guys give me, you know, I might tell the markers to give part marks for this one or this one. But yeah. That's the reasoning I want you to go through. Essentially, the period of oscillation or the frequency depends on what this number here is. Below is a waveform at time t is equal to 0. If the triangular moves to the right at blah, and the square moves to the left at blah, draw the height of the wire at t is equal to 2 seconds. Okay, so where are they? At t is equal to 2, delta x is equal to v times t. So it's going to be 1.5 times 2, so it's going to be 3. So this particular question is testing 2 pieces of knowledge. Well, this is one of the pieces of knowledge, maybe 3 pieces of knowledge. The first principle here is the waves don't change shape. So they're just going to be transposed. This one is going to move to the right. This one's going to move to the left. Let me draw where they are at each of the times before I do anything else. 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So this triangle one is going to move 3 to the right. Why 3? Because the wave speed is 1.5 and it's been going for 2 seconds. 1.5 times 2 is 3. So this one here moves 3 spaces to the right. It's going to keep its shape, but the easiest okay, so honest talk now. The easiest way to do these questions is to track the right-hand endpoint, this part. So start by moving this part 3 to the right. So it's going to start at 6. Okay? This particular shape is 2 things long. It goes up for 1, and then it goes down for 1. So it goes up for 1, and then it goes down for 1. So that's where that shape is going to be. What about this other shape? Let's see, red. This shape here is going to move 3 to the left. Okay, so it's again, track its right hand or left hand endpoint in this case, or you can track the right. Doesn't matter. Move it 3. So 1, 2, 3. That puts it at 5. So it's going to be like this. So what does this shape look like? So the second part here is the individual parts of the wave don't change shape, but then there's the superposition principle. And maybe on your final exam you'll get a slightly better drawing than this, But the superposition principle says the height of the function at any of these times is the height of each part of the wave added together. All right, so that's 4, 5, 6. So from 4 to 5, there's no red part of the wave. There's no square part of the wave. So the wave is going to look exactly the same. It's going to go up like that. Okay. For this part, you're going to imagine them stacked on top of each other. So you can draw the square one if you want. It's going to look like that. And then you can draw the triangle one on top of it. Okay. This particularly works if one of the wave is going under the axis. So, and then what you do is you follow the sum of these two. So it'll look like, first it's going like that, and then it's going straight up and then down like that. It's only going to look like that for a moment because the two waves are passing through each other. So we did this activity in class. I hope you're pretty good at it because it's a pretty fun way to test people. All right, next question. Now we're into the long answer segments. In these ones, sometimes the questions will have me follow longer steps. So break down into smaller pieces. So I might say, do this part, then this part. Or I might just say, hey, calculate the answer. And it's up to you to figure out the intermediate steps. If that's the case, we'll probably be a little bit more forgiving in terms of part marks. But the real reason I often break things down into individual steps is so that even if you don't know what the answer is in the time before, you can still sort things out. Okay, so charge A is here at 2 and height 1. Charge B is at -2, 1. And charge C is at 0, 3. We want to start by calculating the force on C. Okay. So, how are we going to do that? You know what? I'm having trouble scrolling back and forth between all these. I am going to make a diagram. You don't need to recopy all these because you're not working on a stupid tablet computer. But I am. So I am going to write some of these numbers down. So this is -4e minus 4. This one's 7e minus 4, and this one's 6e minus 4. And I'm going to copy and paste this. Like I said, you don't need to copy and paste these over and over and over, but for this question, I think it's going to help me do it, so that's why I'm doing it right now. Okay, and you know what? This question seems fairly aggressive to me. I don't know why I made such a big question. Okay, I want to calculate the next net force on this one. And to do it, I need to figure out the forces from each of these one at a time. Okay? And this was the first thing we did in class. I hope you remember. We talked about how to essentially do this calculation. The idea here is you're going to start by drawing a vector between these. So that's RAC, and it's the position 2i hat plus 1j hat minus, hold on. Maybe I'll go up a little bit more. Okay, so it's RAC is the position vector of C minus the position vector of A. So this is the position vector of A. Here's the position vector of C. It's 3j hat. So together, our AC is going to be minus 2i hat plus 2j hat. And then we're going to find the magnitude of RAC. So that's going to be square root minus 2 all squared plus 2 all squared. Let me take out Calculon, see what it has to say. So that's 2.828 meters. And then I'm going to find the unit vector, RAC. So that's going to be your R vector AC divided by the length. So it's going to be minus 2 divided by 2.828. So it's going to be minus 0.707 I hat plus 0.707 j hat. And now I want to calculate the force AC. So that's equal to K QA QC over RAC all squared. So it's 99 times 4e minus 4 times 6e minus 4 divided by the distance between them all squared. 2.828 all squared. So that's 27.0 newtons. And then for the force, you're going to multiply this number you just calculated by R hat AC. So 27 times 0.707. So it's going to be minus 191 I hat plus 191 j hat. All right, now I need to do it all over again, but for B. I'll do it in pink, I guess. That way. Oh, woof. There's a shortcut to do it, but I'm not going to teach you the shortcut. You got to do the long way. Long way always works. The shortcut's only because I think I got lazy making this question. Okay, so F. All right. Okay, so I'll do it the long way. RCB is equal to 3j hat minus minus 2i hat plus 1j hat. So that's equal to 2i hat plus 2j hat. Yeah? Yep. So the magnitude of that length is going to be the square root of 2 squared plus 2 squared. So that's 2.828 meters. And RCB, that unit vector, is going to be RCB divided by this length. So that's plus 0.707 I hat plus 0.707 j hat. And now I need to calculate the force, which is going to be K times QC QB divided by RCB all squared. So that's 99 times 7e minus 4 times 6e minus 4 divided by so that's 473 newtons. And so F CB or BC, I don't know, as long as there's a B and a C in there somewhere, I think we're good. FBC times, that's this guy, times R hat BC. So that's 7 times 0.707. So this is 334 I hat plus 334 j hat. So F total is going to be adding this vector to this vector. So it's going to be 343. Oh, be nice. Hold on. 334 I hat minus 191 I hat plus 334 j hat plus 191 j hat. 143 I hat plus 525 j hat newtons. There's my final answer. Okay, so while we're at it, some people have showed up. Jean-Philippe Abder says, if we want to do this question using trigonometry instead of calculating the vector first, that's okay, right? Here's the thing about using trigonometry. I'm really good at trigonometry, so I could probably pull it off. I'm not confident that you're good at trigonometry. If you are good enough at trigonometry that you can pull it off and get the right answer using trigonometry, go ahead. If you can't, here's the thing. I'm going to be telling my markers to look at doing it this way, okay? And I'm going to tell them to, like, they're all grad students, so presumably they know some trigonometry. And presumably if they see you doing trigonometry, let's say you don't get the right answer, but most of the steps were right. If they can't tell what you're doing, they will give you 0. Or maybe instead of, maybe if this question's out of 10, and you did 8%, 80% of it right, I would be like, oh, maybe that's an 8 out of 10. That's no guarantee the marker is going to see it and know what you're doing. And if the marker doesn't know what you're doing and the marker sees that you get the wrong answer, sometimes they'll come talk to me and I'll sort it out. Sometimes they'll just be like, oh, well, they're just BSing. I'll give them 2. So you got to be careful when using other methods. I'm not saying don't, because maybe you have a method that you use to understand it perfectly. But if you're not using one of the standard methods that they're looking for, if you're using one of these other ones, I can't guarantee that the marker is not going to make a hash of it. And I'm not going to guarantee that I can stop them from it, because there's 220 of you, and there's going to be lots of pages to this test, and I will have my own questions to be marking. So yeah, can you use trigonometry? It's a mix. If you're not doing it properly, so before we say anything else, it's possible to try to use trigonometry on this, but if you don't know how to apply trigonometry to these questions properly to get the same answer, you're going to get the answer wrong. So it's possible to think you understand trigonometry and still get these questions wrong, okay? If that's the case, God help you. Because not only will the markers give you 0, but if I see you get it wrong, and there's nothing about it that's right, you will still only get 2 or 1 out of 10. So yeah, it's a complicated question. I don't want to say you only want to do things in a way that markers are going to understand. That's definitely what I don't want to say. I want to say understand things your own way as long as they're right, and be able to defend and show every step of doing it your own way and defend that it's right. And if you do that and it's right, you should get full answers. But the honest thing is, you've got markers, and this is the 4th test that they'll have marked, and their eyes are all bloodshot. They're going to be trying their best, but they might miss something. So you can use, this amounts to me saying, is it okay to use a shortcut through the woods on this hike? You can use a shortcut if you want, but if you use a shortcut and you get eaten by a bear, I'm going to be like, sorry. All right, that's my answer to this. Generally, that's true for all final exams, which is why I went on and on about this. Okay, calculate the electric field at this point. Oh gosh, why did I only give you half a page for this question? Oh man, brutal. Okay, you know what? It's easier than it looks. But it's easier than it looks because of symmetry and not because you don't deserve more space. You probably deserve a whole page to do this question. Okay, so the deal here is that the electric field at any point is just going to be, it's the force per Coulomb. So if you think about the Coulomb's law, it looks like this. It looks, all right, so Q times E is equal to F, right? If you look at Coulomb's law, Q times K Q source over R squared. We can call this thing, it's a vector, you can call that the electric field. So essentially that's what we're going to calculate 3 times. The procedure that we're going to use to calculate is pretty much identical to the ones we've been using. Okay, so let's calculate EA. To calculate EA, what we're going to do is, I'm going to put you there. Okay, so first you have to, I'll call this point P. First you have to calculate the vector from A to P. That's right, it's a wrap. That's minus 2 I hat, 0 k hat. So the length of this is going to be square root 2 squared plus 0 squared, which is 2. And so the strength of the electric field, oh wait, and then you have to calculate R hat AP, which is just going to be minus 2 I hat over 2, so that's minus I hat. Where'd this come from? I'm literally doing this thing 700 times. Okay, so it's going to be K times QA over RA squared. So it's going to be 9E9 times minus 4E minus 4 divided by 2 times 2. So that's minus 9.0 E5. And so the electric field vector is going to be this magnitude times this unit vector. So it's going to be plus 9.0 E5 I hat. The minus signs cancel out. So now I just have to do this for all the other ones. RBP, that vector is plus 2 I hat. So the magnitude of this is going to be 2. And so the unit vector is going to be plus I hat. And so the electric field strength is going to be K times QB. Here, I'll write that out. K times QB over RB squared. All right, so that's 9E9 times 7E minus 5 divided by 4. 9E9 times 7E minus 4 divided by 4. Okay, good. So this is 1.58 E6 newtons per coulomb. And so the electric field vector here is going to be 1.58 E6 in the plus I hat direction. All right, and the last one, this vector here, RCP is going to be minus 3J hat. So the length of that is 3. So the unit vector is going to be minus J hat. So EC is going to be K times QC over RC squared. So it's 9E9 times 6E minus 4 divided by 3 times 3. So this is 6.0 E5 newtons per coulomb. And then the electric field strength here is, it's in the minus J hat direction. 6.0 E5 newton per coulomb J hat. Okay, so the total electric field is going to be EA plus EB plus EC. 9.0 E5 I hat plus 1.58 E6 I hat minus 6.0 E5 J hat. All right, these two here are in the I hat direction, so I have to combine them. 9E5 plus 1.58 E6. So that's 2.48 E6 I hat minus 6.0 E5 J hat newtons per coulomb. And that's how it's done. It's a little bit long, but that's the answer. Okay. Calculate the potential energy required to build the system. Oh. Okay, so how did we do this? It was pretty fun. The deal here was you had to build the system one piece at a time. Okay? So bring in A, bring in B, and then bring in C. So to bring in A, what you do is you imagine that there's nothing there. I mean, you imagine that there's nothing at the point you're talking about. You're going to treat that as a test charge, and all the other charges as a field charge. And the thing about this is, that one's not there yet. There's nothing there. Starting with no charges on the field. Okay, so why don't I write on the field? There's no charges on the field yet. So the V at the point A is going to be 0. There's no electric potential at the field. So the potential energy it takes is going to be QA times V, so that's 0. It takes no energy to bring in the first charge. Okay, so then what you do is you say, okay, right now there's only this charge in its place. So on the field, there's charge A. Okay. Now what I'm going to do is I'm going to calculate V at the position B. So I want to know what the electric potential is at this point. The electric potential is actually really easy to calculate. It's K times Q divided by the distance between the points. So this distance here is 2, and this distance here is 2. So the distance here is 4. So it's 9E9 and minus 4E minus 4 divided by that distance there is 4. 9E9 times minus 4E minus 4 divided by 4. So it's going to be minus 9,000,000 volts. And then the potential energy required to do that, to move B into place from infinity, is going to be the charge on B times the V at that location. So it's going to be 7E minus 4 times minus 9,000,000. So times 7. So it's going to be minus 630 joules. Before we go on, this is a negative number. A negative number. Is that bad? Sometimes it's bad, sometimes it's good. In this case, what does it mean to have a negative potential energy? It means that energy was released building the system. These two charges, B and A, both have opposite signs, and that means they're attracting each other. So as we bring it in from infinity, B is speeding up. And then you have to stop it when it's here. And so energy is lost from the system when you stop it. The potential energy turns to kinetic energy, and then you take away its kinetic energy to stop it. Loses energy. Total energy is negative. Bring in C. Okay. So the way to do this one is essentially the same. On the field, this charge is A and B. So the V at point C is going to be KQA times the distance from A to C plus K times QB over the distance from B to C. And you know what? I already calculated those numbers. Where did I calculate them? Up here. 2.828 meters. Okay. So let me do this calculation. I'm not gonna write in all the numbers. I'll do it on my calculator. So that's 7e minus 4 divided by 2.828 plus minus 4e minus 4 2.828 times 9e9. So that's 95478 volts. Okay. And so the energy required to bring in C is going to be V at location C, this quantity, times the amount of charge on C. So it's going to be 95478 times 6e minus 4. 572.8 joules. Okay? So the total, the value that we're looking for at the end of this is going to be the delta U to bring in charge 1A plus the delta U to bring in charge B plus the delta U to bring in charge C. So it's going to be 0 plus minus 630 plus 572.8. Minus 57.2 joules. All right. So that's how to do those questions. I want to give a couple disclaimers here. Let's see. How much is this question worth? Oh, I didn't write how much each question is worth. So if you can expect, how many long answer questions are there? 1, 2, 3, 4, 5, 6, and then derivations. Yeah. So this question is actually pretty long for a question on a test like this. If I were to give you this on a final exam, it would maybe have similar questions, but there would have been fewer charges, or it would have been only one of these 3 fairly convoluted questions, because there's a lot of material here and there's lots of stuff to know. So I'm not sure if I would give you all 3 of these one after another. This is a pretty ambitious question for a final exam. This much work for one long answer question is pretty ambitious. All right, but here we are. Let's do the following circuit. All right, I love these questions. If you can't, I want to know the current through each resistor. So what I'm going to do is I'm going to write down here delta V1, I1, delta V2, I2, delta V3, I3, delta V4, I4, delta V5, I5, delta V6, I6. Okay. So the trick to doing these questions is to effective resistance the question up. Okay, so we're going to break this into simpler and simpler resistor systems until there's only one, and we're going to work our way down the page and back up the way I taught you. So first off, I'm going to combine these 2 together, and I'm going to combine these 2 together. 12 volts. So R1 stays the same. R1E, R4, that's R4, changes, and this is R2E. Combine those 2. It's actually helpful. I1E, R4, delta V4, I4. It's helpful when you're working through this to give yourself the space to write out all this material as you go. R2E, delta V2E, I2E. And before I forget these values, I'm going to copy them down here. So this one's the same. It's 1 ohm. I combine these 2 into this one. So those two, they're in series, so it's going to be 4 ohms. R4 is going to be the same, 2 ohms. And R5 and R6, I combine them. They're in parallel, so I'm going to go 1 divided by 2 is 1 divided by 10, 1 divided by answer. Oh, gross. 1.6666 ohms. 1 divided by 2 plus 1 divided by 10. Right, answer. That's gross. Okay. So now make a simpler diagram. I guess R1 stays the same. I'll combine these two into a single one. R3E. R2E is still there. Okay, so R1 stays the same. Delta V1, I don't know what that is. I1, I don't know what that is. R3E, delta V3E, I3E, and R2E is 1.666 delta V2E, I2E. So if you do the work writing all this stuff down as you're going down, it just saves you all the space and it keeps all the information clear. These questions are super straightforward to do, but the tricky part is keeping track of all of the information. All right, so now I need to combine these two in parallel. So I'm going to use the parallel formula. 1 divided by 4 plus 1 divided by 2 divided by answer. Oh, great. 1.33333. Okay, and that's not even supposed to be a delta in front of there. All right, and let's combine them all into a single one. R4E. Delta V4E, I4E. Okay, so it's going to be, they're all in series, so I'll just add them together. 1.666666 plus 1. All right, this is supposed to be 4 ohms. Okay. And Matthew Mesquita says, Tibbs, are you hopping on Overwatch tonight? And my name isn't Tibbs. Tibbs is is Sidney Poitier's famous character from The Heat of the Night. No. Am I going on Overwatch tonight? No, I have to go to a meeting with a guy to plan fixing the bunny sanctuary. So that's what I'm doing. Okay, physics questions though. Come on, Matthew. All right, so how do we do this? The deal is there's only one resistor now, so the voltage across it is going to be the voltage from the battery. And we can figure out the current using Ohm's law. V is equal to IR, so 12 divided by 4 is equal to 3 amps. V over R is equal to I, right? And then the idea here is we're going to translate this information up the page. All of these are in series, and that means that they have the same current as this effective resistor. 3 amps, 3 amps, 3 amps. All right. Now I'm going to use Ohm's law to calculate what the voltage in each of these is. Okay. So it's V is equal to IR, so this is going to be 3 volts. 3 times 1.3333. So this is going to be 4 volts, and 1.6 times 33333. Oh no, wait, hold on. I did that wrong. 1.6666 times 3, that's 5 volts. Remember every time you do one of these things to check. The rule is that these 3 voltages should add up to 12 in this case, the effective voltage. So 3 plus, okay, so all these, 3 plus 4 plus 5 is 12. Now the trick is I'm going to copy down information from these ones up into this set. I'll use the color green so we can keep track of what I've done. So R1 stays the same. 3 volts, 3 amps. R2 is staying the same. 5 volts, 3 amps. Okay, so R3E turns into 2 that are in parallel. If they're in parallel, it means the voltage across them is going to be the same. 4 volts, 4 volts. That's this number. Okay? And now I'm going to use Ohm's law to figure out the missing piece, the current in each of them. V divided by R is I. 1 amp. No, let's use a different color. 1 amp, and 4 divided by 2 is 3 amps. Nope. 4 divided by 2 is 2 amps. Again, this number and this number should add up to this number, and they do. And now I'm going to copy the information, the pertinent information, up onto this. So R1 stays the same. Part of the reason you might be like, why are you using these E's? The deal here is every time you see a number here without an E in front of it, it means that you can copy that number directly into the final answer. So this is 3 volts, 3 amps, copied straight. R4 stays the same. 4 volts, 2 amps. And now we're going to use the information on this one to make these two. And we're going to use the information on this one to make these two. Okay, so let's go over those. The first one first. This one? Okay, these two, sorry, this is R1E on this diagram becomes these two. So they're in series, and that means the current through them is going to be the same. So let me copy down that current. It was 1 amp. And now, similarly, this one became these two. They're in parallel, so the voltage is going to be the same. It's going to be the same as this number. 5 volts is 5 volts, 5 volts. All right, and now I'm going to use Ohm's law to finish it off. E is equal to I times R. So this is 2 volts, and this is 2 volts. V is equal to RR. Nope. V divided by R is equal to I. 2.5 amps. And this is 0.5 amps. Okay. Those add up to 3. All done. Considering the following circuit, oh, this is a really badly drawn circuit. At time t is equal to 0, I close switch A. Hey, on this one I drew switch A. Congratulations. At time t is equal to 0, yeah, hold on. At time t is equal to 0, using Kirchhoff's law, loop laws, calculate the brightness of each bulb. Okay, great. The spacing on this question is actually pretty weird. I probably should have changed the spacing a little bit. But like I said when I made this, I didn't proofread it. I mean, I looked through, made sure I could do the questions, I think, but I didn't work very hard on the spacing, stuff like that. Okay, so the deal here is we're closing this gap, and we are going to write down Kirchhoff loop laws for each of these. The first step is to write a current name for everything. So I'll call this I1, I'll call this one I2, and I'll call this one I3. So maybe up in this region, I'll write down the Kirchhoff loop laws. First, there's the junction rule. Let's go by this junction here. I1 comes in, and I2 and I3 come out. In is equal to out, right? Next thing, I'm going to take my finger and trace it around this loop like that, in that direction, okay? Again, starting here, I'll go in this direction. I can't show it while I'm writing down all the components, but keep in mind that I am. My finger is on the page. All right, so it's from minus to plus on this thing, so it's going to be plus 12. And then it's in the direction of the current, so it's going to be minus 1 times I1. And then it's in the direction of the current, so it's minus 2 I2. And then I get back home. Now I'm going to do the same thing in this one. You know what? I'm going to put a delta V inside our equations, just so we have a sense of things. I'll call this side plus, this side minus, and I'll call this VC. Okay? So let's go this way around the current circuit. Why not? I'll move through the capacitor just like it's a battery. So it's going to be plus VC, and I'm moving against the current, plus VC, and I'm moving against the current in this one, so it's going to be plus instead of minus. Plus 4I3. I'm just going to go around, and now I'm moving in the direction of the current. So minus 2I2, and then I get back home. So those are my Kirchhoff loop laws. At time t is equal to 0, I want to apply these loop laws to the equation. Okay. So at time t is equal to 0, I know that VC is equal to 0. Okay? So my loop laws look like this. Gotta clean things up here just a little bit. Okay. So I want to figure out what the brightness in the bulb is, and that means I need to know the current through each of those resistors. Let's just play the replacement game. 12 minus I2 minus I3. I'm going to substitute in for that one. Minus 2I2 is equal to 0. And the other one is 4I3 is equal to 2I2. So my first equation up here becomes 12 is equal to plus 3I2 plus I3. This equation here becomes 2I3 is equal to I2. So I'll do a substitution in with I2. So this becomes 12 is equal to 3 times 2I3 plus I3, which is equal to 7. Oh, this is a terrible question. 7I3 in total. So I3 is going to be equal to 12 over 7. Oh gosh, what was I thinking? I thought I planned all this out. I2 is equal to twice that. .428, and I1 is equal to all those three added together. 5.142. Gross. All right, so now it's asking me about the power. Power is equal to I times delta V. So it's, I know what the currents are. So it's V is equal to I times R, so it's I squared times R. So the power in the first one is I squared times R. The power in the second one is I squared times R. The power in the third one is I squared times R. So it's going to be, that one is 26.4 watts. The second one, squares times 2. .5 watts, and the third one is equal to times 4, 11.75 watts. All right, these questions look really weird. I'm going to do a quick side calculation. So sometimes you get the answer and it's weird, and it's helpful to do a side calculation. I want to note here that effectively at the start time, the circuit looks like this. There's no charge on our capacitor, and so it's effectively a circuit like this. So the effective resistance of the two bottom ones is 1 over 2 plus 1 over 4. Right answer. Plus 1. What's my answer? Okay, it's consistent. This is just a really weird question. So I can do another calculation to see whether or not the calculation I had is right, and it is. It's just really weird. After a long time, calculate the brightness of the bulbs. Okay, so let's do this all again, but for a long time later. What do I know about what happens a long time later? After a long time, I know that current stops flowing in the third current. So a long time later, I3 is going to equal 0. Okay? So I can remove I3 from each of these equations. And this is what it looks like. Don't worry about VC for now, because I guess the question doesn't ask about VC. So I can use this to substitute into this question. 12 minus I2 minus 2I2 is equal to 0. So 12 minus 3I2 is equal to 0. So I2 is equal to 4 amps. And then I1 is equal to 4 amps. So the power in 1 is going to be 4 squared, so it's 16 watts. The power in 2 is 4 squared times 2. So it's going to be 32. 16 times 2, yeah. 32 watts, and the power in 3 is going to be 0. And if I cared, VC is equal to 2 times I. So that's 8 volts. And, you know, QC, the charge on that capacitor is C times V. It's 8 farads times 8, 64 coulombs charge on the capacitor. All right, quick note. I didn't ask you in this question what these terms are, and if you're not asked for it in the question, and it's not an intermediate step, you don't need to show it as part of your answer. So you'll note that when I did this question, I took a couple minutes to calculate this at the very end. This question is only asking about the brightness of the bulb, so I don't need to say it. That said, I probably did need to say that P3 is equal to 0. See how that works? Focus on answering the question we're asked. Don't waste any time. Okay, a particle of unknown mass has charge blah, and we want to describe what it does in a mass spectrometer. The deal with mass spectrometers is that when we talked about them in class, we actually focused on this part of it, and I told you that, you know, we knew what the speed was going in. That's not entirely true. We don't know what the speed is, but what we do is you ionize your material, you give it 1 electron or 1 proton worth of charge, and then you put it inside of an electron gun. We talked a little bit about electron guns. They shoot charges out. They're just parallel plate capacitors with a hole in them. It's literally like this. You have a thing covered in negative charge, right? It's a negative parallel plate capacitor. You have another one covered in positive charge. You cut a hole in it. Okay. And then you take your material out here and you release a sample of little ionized material. There is an electric field between these, and so this little charge particle feels a force pushing it forward. And sometimes, if things go right, they pass through that gap. And the deal is, as they pass through that gap, you know how much kinetic energy they have. Okay, so that's what we're going to be talking about today. Let's delete all that stuff. Yeah, whatever. If we place the charge particle with capacitor charge blah at one end of the electron gun, with potential blah, write an expression for the speed of the particle in terms of the unknown mass. Okay, so this is an energy question. The deal here is delta V for the particle is equal to 8 volts. So delta U for the particle. Its change in potential energy is going to be its charge 2e minus 8 times 8 volts. So 16e minus 8 joules. That's how much its kinetic energy has changed. I think probably starting from rest. Should have said that in this. Like I said, I haven't proofread these very good. All right, so its kinetic energy, its change in kinetic energy is it's going to go up by 16e minus 8 joules. And so its final kinetic energy is going to be its initial kinetic energy plus delta KE. Its initial kinetic energy is 0. Its change is 16e minus 8 joules. So the final kinetic energy is going to be 16e minus 8 joules. And that's going to be 1/2 times its mass times its v squared. Okay. The question is asking, what's its v? So I can rearrange this equation. So this is 32e minus 8 divided by m square root is equal to v. That's its speed. Next question. Entering the mass spectrometer, it enters a region of strong magnetic field. Hello, I am now in the region of strong magnetic field. Travels along a particular path. Sketch the trajectory of the particle. Okay, so for this, I wanted you to draw the path it's going to follow. You need to know a couple things to do it. One is that when a charged particle moving at a constant speed, perpendicular to a uniform magnetic field, all this is, it's going to go in a circle. Maybe you remember from class when we talked about this specifically. So it's either going to go in a circle in this direction, or it's going to go in a circle in this direction. And so the question is, which one? And it's going to, essentially, when it goes in a circle, it's the force from the magnetic field, QV cross B, that's providing the centripetal acceleration. So all I need to do is figure out which direction it feels a force from the magnetic field. I know its direction of V, I know its direction of B. I use the right-hand rule to figure out V cross B. It feels a force in this direction. And that means that it's going to go in a circle like that. And so drawing that circle's what gets you full marks in this. Okay, if the radius is 4 centimeters and the magnetic field is that big, calculate the mass of the unknown particle. This part of the question is fun. Okay, cool. So, what do we know about this? Okay. I don't know. Sorry, my stylus is being weird. Okay. So the force. Hey. Oh, it's okay. So the force is going to be QV cross B. We know they're perpendicular, so it's going to be Q times V times the speed times the magnetic field strength. And you know that this is going to be mass times centripetal acceleration, V squared over R. Right? So this question here is asking us about the mass. Yeah? How are we going to do this? Well, oh, I see why. Okay, hold on. I just want a darker color. Okay, good. We're good again, I think. Yes. So, the deal is that some of these terms have been given to us. B's been given to us, Q's been given to us, R's been given to us. They haven't given us M, and they haven't given us V. But I know how V depends on M. Let's go upstairs and recalculate that back out. It's like that. Copy. Paste. This is also a thing I know. Okay? So let's substitute that into this equation. QV, I'll leave that V for a second. I just want to show you times V is equal to M over R times V squared. 32E minus 8 over M. What happened to the square root? There's a squared on that V. So these two M's cancel out. So this becomes 32E minus 8 divided by the radius, which is 0.04 meters, which is equal to 32E minus 8 divided by 0.04. 8E minus 6. All right. So Q, all right, so let me recopy what we know. This expression is equal to this expression. So Q, why don't I substitute in for the V? Just don't worry about it right now, okay? It's easier to calculate V first and then use this equation to calculate M than it is to algebraically insert this in for the other V, just because you don't want to deal with quadratics. So QVB is equal to 8E minus 6. All right, so Q is equal to 2E minus 8. I don't know what V is. I know that B is equal to 8 Tesla. So I'm going to rearrange that, figure out what V is. 8E minus 6 divided by 8 divided by 2E minus 8. So V is 50. So 32E minus 8 over M square root is equal to 50. So 32E minus 8 over M is equal to 50 squared. 2500. So M is equal to 32E minus 8 divided by 2500. That's 1.28 E minus 10 kilograms, which is a very small particle. That's pretty small. Okay, see how that's done? All right, let's quickly review how we went through this. This question and this question and this question are all questions that you've done on previous midterms, and we've covered explicitly how to do them. This particular question is based on material we did in class. I would consider this question actually to be kind of a more advanced question. It requires that you put information that I expect you to know, like this. I expect you to know this. I expect you to know, say, this together in a new way, maybe in a way we haven't gone through in class. It's pretty literal to figure out something we don't know. I'd consider this a fairly advanced question, but sometimes life throws you things that you expect to know, and you know, truly mastering them requires that you demonstrate to me that you can put things together in new ways that you haven't seen before. Don't get too worried about this particular type of question because you won't see these very often. In this test, I think there's only this one and then a little bit of another one. Most of the types of question you've seen before. But I just want to emphasize something here, that in more advanced physics courses, including this one, sometimes you see information that we expect you to have mastered presented to you in new and different ways that require you to kind of think on your feet. That happens sometimes, and as far as university physics class goes, we consider these questions fair game. So if you complain to us, oh, you didn't show us how to do this explicitly in class, we'd say, oh, we gave you all the pieces. And problem solving is one of these things we expect you to learn in physics. So yeah, thinking about things in new and cool ways should be pretty fun. How would you expect to do this in class? Well, I mean, in class, maybe this is kind of a pretty literal question. Not too difficult. All it requires is that you understand the V in a potential is the potential and how it relates to potential energy. how changing potential energy relates to kinetic energy, and how kinetic energy relates to speed, right? That's not too tricky. This question it goes in a circle. You need to know that, but I've been emphasizing that. What about this question? Well, maybe you'll have this expression written down on your equation sheet, and you know what it means. The force from the magnetic field is what's pulling it in a circle. And then you could recognize, hey, on a previous one of these, so in this question, I don't know what V is. They don't give me what V is, and they don't give me what M is. How do I algebraically solve this? You might say, oh, well, they don't tell me what V and M is to solve this question, but I do have another equation from earlier that applies to this that relates V and M. And so you can put these two together in a new way to figure out what the mass is. Okay. Oh, I better hurry up. Okay, running out of time. Calculate the magnetic field vectors at the wire C. Okay, that's not too bad. That's like let's use I'll do it from A and from B. Okay, so quickly now. Sorry, I gotta go in like a couple minutes. Let's use Amperian loops. So let's imagine the magnetic field is going around like around the back, around the front, like that around that one from A, and so it's going into the page on this side. So it's going into the page on this side. So that's in the minus k hat direction. Okay, so let's imagine an Amperian loop that's a circle whose radius is, I guess, 5 meters. R is equal to 5 meters. Okay, so the idea here is the circulation from the loop. So I'm using Amperian loops, Amperian loop laws, Ampere's law. In Ampere's law, the circulation from B, which is going to be 2 pi times 5 times B, that's equal to the total current, or rather this current, going through the system, times mu naught. Mu naught times 20 amps. So the magnetic field strength is going to be mu naught times 20 divided by 2 pi times 5. All right, hold on. I'm going to look up mu naught. It should say at the back of the test, but I don't have that in front of me. Okay, so this is 4 times pi, 1e minus 7 times 20 divided by 2 times pi times 5. That's 8e minus 1, 2, 3, 4, 5, 6, 7 in the minus k hat direction. Okay, so same thing. I am going to calculate the loop law from B. So this one has magnetic fields going around in that direction. So they're coming out of the page in this side, and they're going into the page in this side. So it's going to come out of the page over here. So it's in the positive k hat direction. Where am I getting this positive k hat direction business? I'm looking at this. Okay, so the circulation from of the magnetic field is going to be the radius of the circle. So imagine a big circle centered on the wire. And so the radius of this wire is going to be 3 meters. So it's going to be 2 pi times 3 times the magnetic field strength is going to be mu naught times all the current, in case this one going through it, times 60. So the magnetic field is going to be mu naught times 60 divided by 2 times pi times 3. So that's 4 times pi times 1e minus 7 times 60 divided by 2 times pi times 3. So that's 4e 1, 2, 3, 4, 5, 6 minus 6. It's in the positive k hat direction. Calculate the force vector Okay, so the force it feels is going to be the magnetic field strength. Let's see. It's the length of the wire, current, cross the magnetic field. So I'm going to get the direction using the right-hand rule because they're at right angles. So the magnitude, because they're at right angles, I can just multiply those numbers together. There's 6-meter wires. The current going through wire C is 30 amps. The total magnetic field is going to be 4e minus 6 minus 8e minus 7 in the k-hat direction. So that's 4e minus 6 minus 8e minus 7. So that's 3.2e minus 6. 30 times 6. So that's 5.76e minus 4 newtons. And now I'm going to use the right-hand rule. The overall net magnetic field is coming out of the page. So according to the right-hand rule, I cross B, the force is going to be to the right. So the final answer is 5.76 E minus 6 I hat. Okay, a donkey pulls a rod along the rails. The donkey position is that. And, cool, fun. Okay, so this question is pretty cool. I have to break things down. First, I have to figure out what the magnetic flux is. It's going to be the magnetic field dot the area vector. So what's the area? The area, they're at right angles, so it's going to be the magnetic field strength times the area. So it's going to be 8, which is the magnetic field, times 2.1 times the 4 plus 8t. Okay. So that's going to be 4 times 8 times 2.1, 67.2 plus 8 times 8 times 2.1, 134.4 times t. That's the magnetic flux. All right, so the EMF is going to be the time derivative of phi. So it's going to be 134.4 volts. How much current goes through it? There's a 4 amp light bulb. So the current is going to be 134.4 divided by 4 amps. So it's going to be 33.6 amps. So the power is going to be I times V. Four, 5, 1, 6 watts. Oof, terrible. Calculate the force of the magnetic field on the rod the donkey is pulling. This is a fun question. Let's think about it. Which way is the current going to go? It's going to try to, the current's going to try to make a magnetic field pointing upwards through this to cancel out the downward increasing flux. So the current is going to go that way. Right? There's current in this rod as it moves through the magnetic field, and so it's going to feel a force. V cross B L I cross B. The force is going to push it in that direction. Okay? And so that's the question. That's what it's asking us about. Okay, so the rod's length, Li cross B. The rod's length here is 2.1. The current is 33.6, and the magnetic field strength here is 8 Tesla. 2.1 times 33.6 times 8. So it's 564.4 newtons. Okay. What force does the donkey exert on the rod? There's a couple different ways to do this. One of them is to use work, so you know the power the donkey has to be exerting, because all of the current going through the light bulb comes from the donkey. But there's an easier way to do this, which is that the rod's moving at constant velocity. So the net force on it must be 0. Does that make sense? The net force must act on it. There's two forces. There's the force from the magnetic field plus the force from the donkey. So they must cancel out. So the force from the donkey must be 564.5 newtons in the positive I-hat direction, to the right. Is that a fun question? That's pretty advanced. I think this test is pretty tricky. I don't know. If you're doing well, that's great. Okay, derivations. So how do you do a derivation? The deal with derivations is every line you write has to reflect some new physical principle that you're introducing. So it's helpful each time you write a line of an equation to describe where you're doing and where it comes from. So a charge Q is placed at the origin. The electric field from that charge is going to be Q times K over R squared. I'm going to start at infinity at R is equal to infinity, where I'm going to define V as being 0. Okay? Now, the change in the electric potential is going to be minus the R initial, R final, electric field, dr. This is the relation between the electric field strength and the potential. The electric potential, right? If you move in the direction of the electric field, your potential energy is decreasing, right? So if I'm moving in the direction of the electric field, and that's a positive number, then my electric potential is decreasing. So, so this is going to be Q times K over R squared dr. I know some calculus, so I know that this is equal to QK over R, R initial to the R final, and then take the limit as R initial goes to infinity, QK over RI goes to 0. And so delta V from infinity to position RF is delta V is going to be QK over RF minus 0, right? So V at RF is equal to V initial plus delta V, where VI is at R is equal to infinity. Your initial point is at R is equal to infinity. So V is equal to 0 plus QK over R. See? That's fun. Okay, last question. Oh no, I'm 5 minutes late. Okay, hold it. A cylindrical solenoid has n windings in total. Yes. It has length L and radius R. If a current I passes down the wire, draw a cross-sectional diagram of the system and uses Ampere's law to calculate the magnetic field inside the solenoid. Explain every step. All right, so it's asking me to start by doing a drawing. So the drawing of the cross section looks like this. All right, so dot, 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 X's in these ones, and this represents a cross section of the wire. There is a magnetic field going this way in an ideal solenoid. So that's B. Ideal solenoid. B is uniform inside and 0 outside. Okay. Step 2. It's asking you to use Ampere's law to calculate the magnetic field inside the solenoid. So what you're going to do is you're just going to start by drawing an Amperian loop that goes around like that. It has width W and length L. Consider Ampere loop, width W and length L. Okay, so the circuit, according to Ampere's law, the circulation of the magnetic field through this loop is equal to mu naught times the current passing through it. Each of these is going to involve 2 steps. So I'm going to label the sides A, B, C, and D. Okay. The circulation from part A is going to be the magnetic field strength times L, because the magnetic field and the direction through the loop are the same. The circulation through part B is going to be 0 because the magnetic field is perpendicular to the line in that part. Through part C, it's going to be the magnetic field strength is 0 times L. And through part D, the magnetic field is 0 because the magnetic field is perpendicular to the, maybe instead of line, I'll write the path. On the other side, the current on the inside, there are how many loops? It's going to be, the current is going to be I, the current through each wire, times the number of wires. Okay. So 5. The right-hand side reduces to BL mu naught I. Number of wires where N is the number of loops per meter, right? So if it's it could be a coil with 20 loops per meter or 50 loops per meter. In this case, it is N windings in L length. Oh, geez, I reproduced these letters. Maybe I should have called this capital L. Maybe I should have called this capital L. I'm sorry. BL is equal to mu naught I capital N over big L times little l. And so the magnetic field inside the wire is going to be mu naught I times N over big L. The little l's cancel out. And that's how you do it. Okay, so that's the final exam. I thought that this exam was actually a little bit challenging. I've probably dumbed this down just a little bit for you guys, but you have been exceeding my expectations all term. So I think that you could probably do any one of these questions at any time. If I gave you this test, I wager most of you would do pretty well. So yeah, that's how to do each of the questions. I'll talk to you later. I gotta go pick up some pies.